In this work, we present, for the first time, an unconditional dynamic human avatar generation method called hyperdiffusion avatars. Our approach captures complex, pose-dependent deformations by leveraging diffusion processes in the network's weight space. Previous human avatar generation methods either leverage prior knowledge from pre-trained 2D diffusion models or learn a static representation from multi-view human datasets. To this end, they fail to model pose-dependent deformations by using solely simple skeleton-based articulation for animation. In contrast, our method aims to generate dynamic human avatars with realistic pose-dependent deformations. Here is an overview of our method pipeline. Our approach uses a two-stage training process. In the first stage, which we call dynamic human avatar overfitting, we optimize a set of UNet networks, where each UNet captures a different dynamic human avatar. In the second stage, called network weight space diffusion, we train a diffusion model using the optimized network weights from the first stage. Once this diffusion model is trained, we can sample new sets of network weights, allowing us to generate new dynamic human avatars, as shown at the bottom. Now let's take a closer look at the first module, dynamic human avatar overfitting. In this stage, similar to person-specific rendering approaches, we use calibrated multi-view image sequences, along with corresponding human pose parameters to train a UNet. Once trained, the UNet weights encapsulate a dynamic human avatar and capture detailed, pose-dependent deformations. This process is repeated for every individual in a multi-view human video dataset. As a result, after training on n different individuals, we obtain a collection of network weights, each representing a unique dynamic avatar. This collection is used for the second stage of our pipeline. Now we will introduce the second training stage, network weight space diffusion. In the second stage, we train a diffusion model to capture the underlying data distribution of the network weight space. During the training process, we first add random Gaussian noise to the clean network weights. A transformer-based diffusion model then takes these noisy weights, along with the corresponding time step, and learns to predict the original, clean network weights. Now we will introduce the last part, dynamic human avatar generation. After training the diffusion model, we can leverage it to generate dynamic human avatars. Specifically, we sample new network weights using the diffusion model's reverse process. This results in a new UNet that represents a distinct dynamic human avatar, as demonstrated in the video on the right. Here we demonstrate the reverse diffusion process of one random sample. Here, the denoised network weights are visualized based on the rendering video. We observe that UNet weights corrupted by noise fail to represent a valid human avatar. However, the iterative denoising process ultimately yields a high-quality human avatar. In contrast to existing human avatar generation methods, which typically produce static avatars and animate them using simple skeleton-based articulation, our approach generates truly dynamic human avatars. Our method captures fine, pose-dependent deformations, such as the realistic movement of wrinkles in a skirt, resulting in more realistic animations. Our method also enables real-time rendering of multi-view consistent images from different camera views. By training on a large-scale, cross-identity, multi-view human video dataset, our method is able to generate a wide range of realistic and diverse, dynamic human avatar